Okay. Welcome. I am just starting. Got the input, automatically download it, and now I'm going to read the solution. I mean, the problem statement. Ugh. So this is the example. Let's put that in there. Looks pretty straightforward to parse. Colon, spaces. Yeah, if we, for each line, just extract I think I can do belongs to digits. Yeah, and then group that the input by yeah, it gives me a table like this, and if I eval each, yeah, yeah, so I'll do it. That's the numbers. Take the first two numbers. Oops. Take the first two numbers, we get this, maybe three even. There you go. Okay, let's read the rest. Stole all the operators. Okay. So operators are always evaluated left to right. So the opposite of APL, where it's right to left. And the operators are add or multiply. Okay. All right. So let's look at the example 190. So you can, there's only one position, so that's in between, I guess. That accepts an operator. Yeah, between 10 and 19. Choosing plus would give you 29. But choosing multiply will give the test value, which is 190, which is the output. Okay. The number. Okay. Next one is more interesting. Okay. It's two positions. Yes, in between these two numbers. And there's obviously, yeah, two each, right? We can do plus or minus, plus or multiply in both of them. That's four, but two of them cause the right side to match the left value, the test value. So you can plus 81 plus 40, then multiply by 27, or 81 times 40 plus, oh, okay, interesting. Yeah, they have to be evaluated left to right. Yeah. And for 292 can be solved in exactly one way, blah, 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 okay. And of the input value, only 3 of the above equations can be made true. So we need total calibration result, which is the sum of the test values from just equations that could possibly be true. Okay, in the input, it's 3749. All right. Looks straightforward. Looks straightforward. Okay. So what can we do? Which one was the valid one? The first one. Let's go with the second one. So one take 326781. Yeah. All right. So what can we do here? Going to be some sort of function that yeah, that takes this number, right? First one, how about we reduce? So we can reduce, right? So essentially W is some sort of sum, right? Then A, B, C, D, E, right? So we start at A, and so we start on the left, right? And we take A and B. We can either add them up or multiply. Okay, so that's what, 2 to the power of possibilities, right? Let me just see. Length of W, if we drop 1, and 2 to the power. Yeah, so that's many options. What about here? Oof. Some of these are pretty big. Nah, 40, 96. Yeah, still a lot. A lot of options. It's a lot of, the solution space is relatively big. Like, honestly, what is the sum? It's not that big, 500,000. Still, I feel like we should try to optimize. So again, we have A and B, right? We take that, we add them, right? That's one value, that's one string. Then move on, right? Or we multiply it, right? And those are the options, right? Eventually, we will have something like just some sort of, x, right? And just the last value. And here we can also either add or multiply. Now, okay, so how can we reduce solution space? We could try, the multiply will always be a bigger number to multiply. So if we go greedy and we multiply, well, that will tell us if it's we'll go over the starting, like the sum or whatever, what do they call the first number? The test value, right? So S capital is test value. We can check. Yeah, we can go greedy and we can just multiply first. Similarly here, we multiply first. That's one, and then eventually we'll go over the test value and be like, hey, that's a wrong branch of the solution space. Stop it. So one way. With adding, there's not much we can do, right? So multiply. So just to understand what's happening here, so if this is a plus, right? Eventually, if this is a plus, we're testing essentially that t is equal to a, b, c, well, let's say plus, right? Let's say it's all pluses, plus reduce, right? Because this will actually add these ones. That's on the wrong order, right? B plus A, C plus, right, if we were to convert this to APL, D plus, E plus, A, B, C, D, E, yeah. So if we will convert to APL and then we check if it's equal to T. Okay, but what if it's multiply, right? Multiply. So once we get this value and we multiply by E, at the end, we either multiply or add. But at the end, the last value we can check if it's multipliable by E to get T by checking if T is divisible by E, right? Yeah, okay, all right. Okay. Yeah, this is better. All right. So if I start at the end, right? So instead I get this, right? And I check if T is divisible E by E, right? Modulo, is that? If E is a modulo of T, then check, so we don't do this, we remove E, right? And we divide, right? We just recurse into this, right? If otherwise, so there's no otherwise. Okay, we can implement otherwise. Yeah, that's fine. Yeah. Okay, otherwise what do we do? We gotta get rid of E by subtracting it from T, the total, right? Because coming from the other end. And yes, eventually we get a X, right? And then here, I mean, we can do the same thing. If it's divisible, yeah, we just keep going all the way. Same thing, if it's divisible, then eventually, actually, we get nothing, right? And here we just check if T is equal to 0, right? That's it. Because we just reduced it all into the T. Yeah, okay, this is nice. This is nice. Okay, so that's the plan. So, test case, if length of the input is equal to 1, so the input is 4, right? If it's 1, then check if the first value, right, or whatever, is equal to 0. Yep. Okay, by the way, right. It will not work. 42. What happens if I have 1 take from iota 5, right? That's a 0, right? But is that, so it's an array, we took 1 off, right? Is it equal to 0? It is not equal to 0. So we have to take the first one. Yeah, okay. So, all right. So, list of, we take the first one, we check if it's equal to 0. Otherwise, we need to check if it's if the first value divided modulo can I do one take of this, and negative one take is 27. What is 27? Is the last one. Yeah, okay. One take each. Yeah. I don't know, this is looking really weird. Oh, I know. Leftmost and rightmost. Yeah. And then if we do the, we need rightmost, leftmost, modulo. What are the values again? 3, 3, 2, 6, 7 divide. Oh, yes, 0 is good. 0 is good. 0 is good. Modulo. Yeah, I was like looking for a boolean or something. 0 means they're divisible, right? So if this is equal to 0, yeah, and also 1 is for the sum, we'll add a sum, okay? So this, the first one, yeah, how do we do this best? Okay, then we also take this operation. Honestly, maybe it's better to just t and last te, right? So t will be, oh, no space, t e, not e, and this is t, x, call it x. So t is the test value, x is the thing. So then x modulo t, right, equals 0, and that's our thing, right? But now I actually do t divided by x, and also we want to t subtracted x. Yeah, okay. Then we choose from this e modulo t. Not e, x. Okay. We select, yeah, imagine if it was not divisible, right? Let's make sure it's equal to, I don't know, 7 remainder, right? Now we just have 1. Okay, so that's one of the t's. So t now is this. Then we recurse into what? We keep the input. We drop the last one because we just used it up. And at 0, we place a t, the new t. Yeah. Right, because this could be t is multiple. So t each. Is there a better way? So I want to recurse with this value where with the first okay, one drop. All right, so that's just the remainder, and then t each concatenate with this group. There you go. So we have this is the input value, right? Just so I don't go crazy. So we got rid of 27, right? We divided 3267, we subtracted it, and we divided into it, right? Yeah, okay. Feel like it should be in reverse, but doesn't matter, right? Doesn't really matter. Doesn't matter. I'll try it both ways. All right, so these are possible so we recurse and what do we recurse? Or reduce. Recurse each. So t. This will do. So we have all kind of possible things. For each one, we for each t, we concatenate it with the thing and recurse, and hopefully we get back the or value, right? This will give us true or false. Here's another one. Here's another test. If t is less than 0, then we're done. 0, that's 0, just don't even try it. So that's a 1. That's an interesting optimization. If we got negative, we've been subtracting so much, it's negative, just done. Okay, so I think we should be ready to run it for all of them. So there's, yeah, first, second, and last. Is that right? 292, yeah, last one. Sounds good. Okay, so we don't need this, and nice. Okay. Then we use that to select from n and first each and sum 37 49. Okay, and running for production. Oof, that's a big number. Is that right? That looks scary big. I'm gonna try it. Okay, that was good. That was a valid number. That was a real number. Interesting. All right, before I continue, let me just clean up a little bit so we don't need display here anymore. Let's keep it for now in case I need it. Let me try. So it runs in what? 200 milliseconds, 280, 270, 250. 250 is the fastest I've seen. What if I don't do this optimization? I'm just curious. That doesn't do anything. Okay. Right, because we always explore. Oh, no, we don't. Okay. All right. What if I reverse? Does it matter? That doesn't matter, does it? Because I recurse into each one anyway. Yeah, still fast. Okay. Right. Don't need it if I don't have to. Okay. Yeah, all right. Let's do part 2. Okay, engineer seems concerned the total calibration result you gave them is nowhere close to being within safety tolerance. Just then, you spot your mistake. A well-hidden elephant was holding a third type of operator. Okay, concatenation operator combines the digits from its left and right inputs. For example, 12 concatenated with 345 is 12, 3, 4, 5. Okay. Also, still evaluated left to right. Apart from the three equations you could make that could be made true using only addition and multiplication. The above example has three more equations that can be made true by inserting operators. Okay. Yeah. All right. 156.56 can be made true through a single concatenation. Right. Yeah. Okay. So this one wouldn't work. This one you would multiply first, then you concatenate, then you multiply by 15. All right. In 192, I thought 192 was already true. Oh, no, that's 292. Okay. 192. Interesting. Okay. That's okay. Okay, so we're going in the reverse. How? So I have 156, right? And I have the last value is 6. Well, that's easy. Just check if it ends with 6. All right. Okay. So same thing. Let me go back to this input. I'll get rid of this because I don't need it right now. I can always add it back. And here instead, what was the 15 and 6? That's a third or fourth, but third. So 3 take. Just return W 15. Okay. Okay. So if the value is this, if there's only one value, then set it to true. We take the first and last, and we just check again. X and T, just return it. Okay. T ends with X. Okay, so I can take T and X, and I can, what can I do here? Not to 10 print. Isn't it just which one is it? This one, right? 6. Suffix. How do I check PPL card? Ends. Okay, this is complicated. So what if I do this? So that will run stringify for both and do something for the rest. So let's just append. Yeah, it just appends it. I just need to check if it ends with it. Cannot terminate. Okay, that's some other stuff. Number of digits. So we can. How do I check? Oh, if it. I can check if it exists. If I reverse. If I also reverse them. What does that do? What? Yeah, okay. Yeah, we get 6 and 516, right? 6 and 156 becomes 651, and then we have a 6. And then just check if they the thing belongs in the other thing. Yeah, And I just need to check if it starts with 0 or with 1. Yeah, okay. And if I run it for each and only one of them works, that checks out. Kind of. That's a really weird equation here. Okay. Stringify, reverse, each, both, then exists in first. Meaning in the beginning, right? Or at the end, really. Yeah. Okay. Yeah. So we can put that together, this whole thing, right? So we try to remove, that's our first test, and we divide. Oh, wait, sorry. That's the wrong one. T and X, right? Then we also want to do the modulo. Oh, okay. The test is here. So the test is X and T. So we don't need to do the reverse here. Oof. Oh, right. This work, and then modulo. So give me a modulo. Okay, so cannot be divided. Yeah, so it can be decode. Well, you can always subtract from it. Yeah. Okay. So that will be our selection matrix, right? Which ones to do. Now, T and X. So we've done minus and divide. But we also need to do the one where we remove the last digits. Okay. So what can we do? Isn't it just, no, we subtract and remove that many zeros? That's one way. Yeah, that would work. That could work. So how many digits is X? What's the log? Come on, log. Natural base n. Okay, 10. Where's the log? Here, right? Okay. Let's just test this. Iota 20, right? But base m logarithm. This logarithm, yeah, that's a log. 1 plus. There you go. And if we ground it and choose from its value, I don't think we get this. Yeah, okay. So this is omega chosen from. So yeah, okay, there you go. So where it's 1 is here. Where it's 0, it's all the. So when you round down and then add plus. Yeah, okay. So if it's a 9, by the way, it will fail for 0. Yeah, it will fail for 0. Why would we have a 0? We would not have a, would we have a 0 there, ever? Okay, and each in 0, no zeros. Yeah, no zeros. What about this one? No zeros. Yeah, no zeros, so we don't have to worry about zeros. Good, because log of 0 doesn't work. And so if we have a 4, right, or 6 in our case, right, that will give us 1. If we have a 26, that will give us 2, and if we have 156 or something, that will give us 3, and this will give us 4, etc. Okay. Yeah, that's doable. So, so we have, well, let me actually take the input. Right, so these are the inputs. Bum, bum. Rounded. What? Maybe it should just be a proper function. Yeah. 1 plus will give us number of digits to drop, and is it possible? And we just divide by that many tens. So 10 to that power. Yeah. And divide. Our number will be 1, 2, 3, 4, 5. Divide that into alpha. But not just divide. Yeah. Technically here, right? Okay, yeah. So what do we try? 6. So we drop the last 4. Yeah, okay. 123, 120, 100,230, 12, 300. Okay. Yeah, this is a little weird, but might work. So now we have this function, but we also want to divide. Get rid of this. And subtract. Right? Yep. And we still do the selection business. What? Oh, just selection, yeah, okay. Okay. Yeah, and that's the new T's. All right. Okay, so if we do this, that should give us 1, okay. We run it for all of them. Oh, great, great, great. Somewhere it doesn't work. Somewhere it doesn't work. Maybe this is where we need to check that T. Just print X's. X and T. Ooh, interesting. 6.6. Okay, and which part is breaking? The main error. Yeah, it has to be log. Has to be log. You know what? Can we make it simpler? I feel like this is already super complicated. So G and X, we stringify 6 length, stringify both, right? And then we get AMW, which is this. We measure length of W, negated, drop from alpha 15, right? Yeah, we dropped last one. Yeah, maybe that will work. And of course turn it into a normal value. All right, so we can add it. Yeah, so it's a number. Yeah, I like this more. So where are we putting this? In here, right? Yeah, this whole thing. There you go. It's a little shorter and no log, so don't have to be weird about it. No result. Was provided. What are you talking about? T? Okay. What do you mean no result was provided? So we get 156, 15, and 6. And we tried minus, obviously, that's just 150. And we tried removing 6, which worked. We get 15. Yeah. And why is there no result found? What does that mean? No result was provided when the context expected it. What the hell are you talking about? Oh, okay. All right. Right, so we tried 156, 15, and 6. We tried removing 6, so we have 150, 15. And we tried 15, 15. That's just a simple... Okay, so when we have 15, 15, oh, I see what happens when it's exactly the same value. Honestly, if it's 2, if the length is 2, so just run it 15, 15, right? If the length is 2 and equal reduced W, it's a 1, right? We have two numbers that are like the same, 15, 15, right? It's like, yeah, you can subtract 15 from 15, done. Will that help? And each, nope, still doesn't like it. Where are we failing? 32, 81, oof. Yeah, so if honestly, if x is more than t, we're done. if t is less than x, done. We're over. 78 and 17. What the hell? What's your problem? What's your problem? 78 and 17. Well, that one's easy. The length is... Okay, the length is 2. Hey, Meatball. How did I get interested in the language? Good question. I don't remember. It was so many years ago. Um, yeah, don't remember. I, if I remember correctly, I wanted just to try something different from just like normal Algol languages. This is, I remember like 15 years ago when I got into Lisp, like in Scheme and things like that. That was very different. And then after a while, it just became not as unique anymore, not as interesting, not as different from the normal uh, way of doing things because functional programming became part of mainstream, and then APL and others were like a whole different branch altogether. So I wanted to see what's so special about it. Yeah. What about you? Are you interested in the language or? Yeah, very much different from imperative. Very much different. Um, you've used Fourth Lisp, RPL. Yeah, yeah. Use more symbols. Yeah, these symbols are like this is a thing before even um, before UTF existed. So these are like they were added to UTF in the end, UTF-8, yeah, but they did not exist. They were not like part of ASCII, obviously. Something's wrong here. I feel like I'm missing. So I calculated. I did the solution first with the optimized way. That's what I thought. How do I? Yeah, for the symbols. Yeah, I have it. I have a special keyboard. I don't know if yeah you can see it. Yeah, special keyboard layout where using what did I use? Unicore? No. What is that keyboard layout making tool called? Um, ukulele. Ukulele. Yeah, ukulele. Ukulele. Like this, I think. Yeah, layout. Layout. No, come on. Keyboard layout. Yeah. Keyboard. Whatever. One of these. It's an app. You can make your own layout, and it's not an actual ukulele. It's the app. Ukulele. That's why. And just made my own. Yeah, there you go. I made my own where like Alt, in my case, Option does something, and it's different from the normal APL keyboard. Space Cadet. Yeah, you can buy them. You can buy custom keyboards, but I don't know. That seems like a lot. I just install this layout. I think it's in my Dropbox somewhere. Just it works for me. It's different from the main one, so I'm not gonna. It doesn't make sense to share it. Anyway, yeah. Anyway, so I solved the problem with the backtracking approach, but it was too verbose, so I got the star and whatnot. But I'm trying to see if I can solve it just like left or right, and it looks so much simpler. I just need to figure out why the last one is wrong. Space Cadet is an older, much bigger keyboard. Space Cadet keyboard. Oh my, okay. Oh yeah, okay, all right. Makes sense. Symbolics. Yeesh. Okay, yeah, that's fancy. quote overstrike. Yeah, overstrike. Yeah, that's fancy. Yeah, mine is a little different. Like, actually, mine is completely different in terms of layout for the symbols. But oh, there's a thumbs up and thumbs down in there. Nice. And left and right. Okay, this is cool. This was used what for? List machines. Okay. But why did they need to keep? Yeah, for YouTube videos. That's right. That's pretty cool. I guess those were the cursors because there's a left and right pointer thingamajig. Yeah, that's cool. Lisp machines used it, but do they mention APL in any way? No. Yeah, I don't know. Interesting. Yeah. Anyway, I gotta finish this. So the naive approach is basically what's it called? Just depth, breadth first search essentially. Just goes all the way in, generates all possible numbers, like here. So it's a reduction, plus or minus at every step with the next value, and just that's it. So something's not working. So I have 190 is correct, 3267 is there, 292 is there as well, 156 is there, 7290 is not there, and 192 is there. 1, 2, 3, 1, 2. What is? Why didn't this work? 7 to 90. 7 to 90 was row 4. Well, 5, but so 4 take. Yeah, I did that right. This one. Yeah, doesn't work. Okay, why not? What are possible values? Print this. Honestly, I'm gonna get rid of this code because it was not very nice. Too long. Print input. That's the input 7 to 90, 6, 8, 6, 15, and for some reason these are all the possible numbers, and 7 to blah 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 is not in there, even though it's possible, right? Because you can do 17 and 8 plus 4. What's wrong with that? Let me just deconstruct this a little bit. Let me save it without printing. Yeah. Okay, so what is wrong with this input? So we take yeah, T is going to be that number. Let's use display here. And these are all the possible numbers. So we return last one. I'll drop one. Got the result on the left using the numbers on the right in the order they're given. Oh, this is what you did? Placing exactly one off between them and evaluating left to right. Yeah, that's right. So for me, so I drop one, so 6, 8, 6, 15. This is what I have as an input. I don't need to print this anymore. Then I reverse it because reduction works in the reverse. And all I do is, well, let's try just this for now. So this will just append them. So 15, no, it's 6, 8, 6, 15. So it appends it in the reverse order, obviously. But I also need to also do a plus. For some reason that doesn't work. Oh, multiply. Multiply is the only operation that is also needed. And why is none of this equal to do an exhaustive search trying out all possible 3 to n minus 1 cases where n. Yeah. So I don't know if you saw it earlier. I had an earlier version where I did like I went backwards, right? So I said, okay, we need to come up with 7 to 90, right? Okay, well, at the end we have 15, right? So at the end we're multiplying something. Either we're multiplying something by 15, or we adding 15 at the end, or we adding or just summing up with 15. Now we can't be appending 15 at the end because there's no 15 at the end of 70 to 90. So that can be, so the last operation cannot be append, right? Then, okay, can we have multiply by 15? Well, that's easy to check. Is this number divisible by 15? If it's divisible, so that's kind of the way, right? So it's not exhaustive because it will not try to do different things. But that was too verbose. It was pretty fast. So now you're looking for an answer that can be given, that can give the intermediate result. Yeah, exactly. So just going backwards, and eventually you end up with, what did I have? Yeah, eventually I need to reduce it all the way to 0, right? Because I will have added, 15 at the end, right? Or multiply by 15, blah, blah, blah. And then the last one was just a 6. So I would look at 6, see what I can do. And eventually I should end up with a 0 because that's what I started with. If you think about it, like there's a 0 in the beginning. No, I check if whatever. If the last one is last two values are the same. Anyway, but that was too verbose because to check if it's divisible and blah blah blah, and if it ends with the same digits, it was too verbose, and I'm just trying to keep it simple, and it seems like it will work fine because I did a simple like input here, just a brute force, and it worked just fine. So except for one of the inputs that doesn't work for the second part. So for some reason, if I use multiply and append, I cannot come up with 70 to 90. How is that not possible? I get the main idea, continue your thing, you're optimized. Yeah, I'm just rewriting it completely. I just got rid of the old code. Maybe I should have kept it. You know what, I'll keep it because I feel like it might come in handy. Yeah, so that was the old code. So that's part 1. And this was part 2. Anyway, I'm not using it, so I'm just gonna remove it from the screen here. Okay. Anyway, so why doesn't using add and append not work for me? All right, what is 6 times 8 is 48. So imagining we have 48, let's do 70 to 90, doesn't matter. So we actually started with 48, and we have a 6 and 15. And would this work? 70 to 90, okay. So that works. Is it because no, that doesn't make sense. Okay. So that makes sense. 1 drop omega reverse. And so we go from 48. 48, we append so if we had 6 and 48, 48, and 6 at the end. Right, and then we multiply by 15, right? That gives us 70 to 90. Why didn't this work? 70 to 90. But if I have 6 and 8 here at the beginning, is t in why doesn't this one have 70 to 90? That makes no sense. Why not? Okay. So first one 8 and 6, right? 8 and 6. So we add it up. That's 14. Yep, double 7, yeah. We multiplied and we append, so 6 and 8, right? So if the first one was 6 appended to 8, 6 and 8. Okay, then, so these are the next values, right? So next values, we look at 6, right? So we look at 6. Now here, we, what if I just do this? Yeah. So here I have 20, 54, 74. So this is taking 14 and adding 6, multiplying by 6, apparently 54, 14 times 6, 84. No, right. So these are, so imagining we have a 6 and we try adding 6 to all of them. So that's 20, 84. I'm already lost. These are all the values, right? So we're trying to add things. Yeah, okay. So we add 6 to them, we get this. We multiply them by 6, we get this. And we append, we also append stuff to it. We get some, don't know. Welcome, welcome. Wizard with a cat. Hello. I assume you guys already solved Advent of Code puzzle. I'm solving it in APL, if anyone's curious. Hey, hey. How's it going? Nice. Odin? Okay, cool, cool, cool. So I solved it in APL. I went with the backtracking approach, and that was pretty fast, but it was ugly. It's right here. So I got the stars, but I'm just trying to solve it in a more APL-y way, maybe. Just like simpler. So essentially, it will just be this, but it's a little slow. So if I just get rid of this right here, it's a little slow. Yeah. So if I can get this to work quickly, I'll be so happy, and I think I might be able to. So first part is pretty fast, but the second part takes like 10 seconds, something like that. See if I can get this solved, optimized, is what I'm trying to work on right now. Anyway, yeah, 14 seconds is how long it takes, but it works. It works. Anyway. Oh, actually, no, it doesn't work. It doesn't work. There's a wrong number here. Huh. Yeah, all right. So it doesn't even work. Yeah, not happy with this. It's both slow and doesn't work apparently. All right. Yeah. Log. I did log. I didn't do log per se. I tried to do log actually. And it would fail for like weird edge cases where there's like a log of 0 and doesn't work, things like that. So I just would add like a 0 right here as a string, and before I evaluate it, just in case it becomes an empty string. I don't know. It was really messy, and that's why I really don't like the solution. It's just messy. There you go. But honestly, otherwise it worked real fine. Actually, this would be, yeah, I don't know. I prefer this way more. Yeah, this runs, right, because what do I need to do here? I already forgot what I did. For each first, and choose from first each, sum up. One was, and did I changed the way I parse so many times now. Yeah, I will probably go to the original solution. The first one was really slow. And also wrong. So I'm not gonna go with this. Okay, parse. Oh, I remember I changed it so many times. Yeah. Yeah. One shift was it? Is that how? I don't know. Yeah, one shift. So I would put the if it's 2, then I just check if they're equal. So if I have 2 data elements remaining, I just check if they're equal. Otherwise, because it's either append, yeah, it just has to be that. Otherwise, I take the last two values, it will be either some sort of tail and the total, check that t is less than 0, and then I do this weird manipulation where I check if it's divisible by 0, or modulo, yeah, divisible by 0, or if it ends, this is a really weird one, if it ends with the strings, and then I do recursion here. Oops, something's wrong. Divide by 0, what? Oh, okay, I remember now. That's why I messed it up. So for each n, it just checks, just returns w, okay. Yeah, I'm just gonna refactor this solution. It worked really well to give me the solution. Okay. Oof. This is the input. How does APL handle errors? You can do that. So I think that's what I originally did. It's really weird. You need to like figure out what's the error type. So for example, index error, I believe, is 3. Domain error, like you saw, I got domain error earlier. That was like some other code. And then you'd put something like before, like in the beginning of the function, you'd put something like, if I get a 3 error code, you do like double colon, then return oopsie daisy, right? I don't know. Something like that. So you return, like this is try catch basically, but you put it in the beginning. It slows down the program a lot because now there's like that try catch thing that always keeps looking out for that error. Doesn't slow it down that much, but once if you can remove this, it like speeds it up. At least in my case, for day 6, it's sped it up by like 5%, something like that, if I remember correctly. So I used it for when we were traversing the graph for day 5 or day 6, right? When you're going through the map, I would just go like blindly and say, hey, just look for, move up, move down, and if it's outside the map, you get index error, and then that means it's you're done, right? You're done with the left the map, right, or whatever it was. Anyway, yeah, that's kind of how you can do the error handling errors. Anyway, just gonna restore this input. So just so that clear, so the input here is some sort of values A, B, C, D, right? And then the total test value will be at the end because I shifted by 1. And what I do is, instead of going like, oh, let's start with A, multiply by B, or add B, or concatenate B, what I try to do instead is check if D can be, if test value can be divisible by D, or it ends with D. And if so, then I just rerun the same with a new test value where it would be like divided by D, right? Or subtracted D, something like that. Anyway, so if we have only 2 values remaining, then I just check if they're the same. If I have and then yes, so I take the last, oh, negative, there you go, that was a problem. So I take the last 2 values, they will be either some sort of value and the test value. I check if t is now less than x. If it's less than x, then I just give up right away. It's 0, meaning false as a Boolean value. And then let me check to the first one, because I remember that working correctly. A bunch of zeros. Okay, great. Okay, why is it not working? Yeah, so the test value is going to be all of the numbers here, 190, 3, 2, 6, 7, yeah, etc. The x value will be initially like the last value, 1927. Then we do for x modulo t, check if it's equal to 0. So if it's divisible by 0, and I need to have a basically Boolean matrix, right? If it's divisible by 0, if it's subtractable but from 0, if they're divisible or subtractable. 1 is always there because it's always subtractable. And then I choose from minus or divide this value, right? Either we subtract with the last point or divide by it. And there will be some, in this case, that's not a problem, but in some cases it will have divisibility errors, but in this, oh yeah, so if I don't do that, right, there'll be some things like that. So this is if we subtract, this is if we divide, but here it's not divisible, so we get this garbage value. But if I select the ones that are divisible only, I only get the 78, right? And then that's my new t value. Same thing. And then there you go, that's the problem. I drop the last two values. I append at the end the new test value, and I recurse. There you go. Okay, so that works. So that worked. Changed the format so many times now that yeah, I think I would rather do it like this and reverse it. So it's actually going to be T, D, C, B, A, right? And that's how it's being called, right? That's the function. So now this is flipped around. Take the first two. Take the first two, and do I need to do this anymore? Yeah, there you go. And we select from the input and only take the first values. Sum up, we get this. Beautiful. Yeah. And for part two, it's the same thing, but yeah, and it runs pretty quickly, right? Yeah, 300 milliseconds, pretty good. Going this way. So I just need to refactor it a little bit. So what I would like, yeah, so the only change that happens is this, the new t. So what I will do is pass in, so I'll make this as a function. I'll make this a function, call it solve, right? And all it does is run it for the input. Well, we'll call it n, right? And then we call solve with n, only with one input. Yeah. Don't need this. Yep. But I would like to pass this as a function to it. So I will take that, pass it as a function that takes, well, how do we do this best? A, W, W, something like that. right? And then this will pass that as a function to the inner function, which we'll just call it for the t alpha alpha x. That work? Nope. Yeah, tx. Right, because this is w, this is, yeah, there you go. And yep, and then now I just need to put this guy inside here. And again, x will be w, alpha, omega, and t will be alpha. That work? Yeah. Yeah, something like that. It's a little better already. Sum of the first values of n chosen from the ones where this alpha alpha function works, passed to this inner function, returns a 1. And it returns a 1 when either we end up with two values and they're the same thing, or we grow, we go over our target value. Yeah, actually, less than or equal, right? Same thing. Again, running this 92 something something 92, is that right? Yeah. Oof. I broke it already. I broke it already. Okay. All right, it works. It works. Okay, I'm not gonna touch it again. It's not as pretty as I would want it to be. I'll maybe spend some time later on to see if I can optimize part 2 a little bit, because I really don't like this really long equation. Don't like it. I think there might be a way I can optimize it a little bit. but maybe make it tacit or something. I don't know, that will probably make it worse. Anyway, yeah, so I think we're good here. I'm gonna commit it in a second and push to my repo. You can check it out if you want. I yeah, guess that's it. I'm going to send you guys to a friend of mine, well, Twitch streamer, raid to Bad Cop. Hopefully you like it. We're solving it in Bash. So cool. And all right, ciao ciao. Bye. It didn't work right. What do I need to do here? Right now. Oh yeah, I have to wait 5 seconds. Yep.